All right, everyone, this is part 2. So in the last part, I showed you what a sigma notation was and how it was a sum. And you start at the bottom, stop at the top, plug in. And then I showed you one result, the fact that this, if I have the summation from I equals 1 to n of I, right? That equals, let me make sure, that equals n times n plus 1 over 2. Okay. That was the result from last time. Just make sure. Yes. Okay. So this is the second part. Well, now that we know this is one thing we'll have to carry in order to do the final thing I want to do. But we need to prove something. We need to prove this other result. That from I equals 1 to n of I squared equals, and this one is n times n plus 1 times n plus 2 over 6. I'm not going to verify it. You verify it as part of the discussion. So you can plug in any number for n you want and verify it for yourself. Yeah. So if you plugged in like n equals 4 here, show me what this left side equals, and then plug 4 into the right and show me what the right equals and show that they equal each other. Okay. That's for you to do. But I'm going to prove to you that it actually is true. And then you're going to just verify it yourself. Okay. So this one's actually going to go very similarly to what we did last time. So I'm going to start with this result. I plus 1, so this is the proof. I plus 1 cubed is equal to, well, if I cubed it all out, you could trust that it's I cubed plus 3i squared plus 3i plus 1. Yeah, it's Pascal's triangle. It's the whole, this thing. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. It's this line, okay? It's called the binomial theorem. I'm not going to go into that. I'm going to subtract the I cubed to the other side. I plus 1 cubed minus I cubed equals 3i squared plus 3i plus 1. I am going to do the same thing I did last time, where I am going to sum from I equals 1 to n of both sides. Okay? On the left, just like last time, you can prove that this is telescoping. That's the second thing I want you to show me when you do the discussion. So I want in your work you to show me that this is telescoping the same way I showed you last time. So this is number 2 discussion. You show me. So number 1 is verified. Number 2, you need to show me this. In the middle, you're also going to, that's fine. I guess we'll just do small pieces. I haven't decided yet. Anyway, you need to show me somewhere in the discussion. I'm going to ask you to show me that this is telescoping. And you're basically just left with the following. You're left with I plus 1 cubed minus 1, just like last time. So that whole left side's pretty cool. All the middle terms cancel. You're left with the, and it's not I, it's n, sorry, because you would have plugged in n. You're left with n plus 1 cubed minus 1 on that side equals, just like I did on the last one, I'm going to split this up into 3 summations. I equals 1 to n of, I'm going to take the 3 and put it out, I squared. Hey, look, there's the thing we want to look for, just like last time. Plus, I'm going to take the 3 out again of this one, just like I am allowed to do, of I, plus the summation, and I equals 1 of 1. Okay, so now the cool result. FYI, little side note for you guys. What we did last time, where I proved this thing here, if you have a proof that relies on a previous proof, which we're about to use, you can show the first proof, and it's called a lemma. So a proof within a proof is called a lemma. So I would say then, if I was doing an actual formal mathematical proof, at this point right here, I'm allowed to say what I already proved earlier on, that the summation of I is n times n plus 1 over 2 by the lemma. So a lot of times we'll say by the lemma, because we proved it. So we proved it earlier on, and now we're using that result. That's why this is part 2, because we already did this in part 1. So essentially in part 1, we were proving the lemma. And part 2, we're actually doing the proof that I need. So pretty cool. That summation's gone. Plus, we did this one last time, and I explained this part last time. If I sum from 1 to n, I have a bunch of 1s I'm adding up n times. So that's n. This is the result I'm actually looking for. So I'm going to leave that right where it is. And I am going to then multiply all this out. So this would be just like we saw earlier, kind of n cubed plus 3n squared plus 3n plus 1 and then minus 1. So those cancel. So n cubed plus 3n squared plus 3n. Cool. Get the summation of I squared by itself and you're done. So I'm going to first multiply everything by 2 because I don't want to deal with this the rest of the problem. So I'm going to rewrite it and multiply every single term by 2. 2n cubed plus 6n squared plus 6n equals 6 summation from I equals 1 to n I squared plus the 2 is now gone here. So I'm going to multiply this out. 3n squared plus 3n plus, and then multiply that back 1 by 2, 2n. All right, almost there. Get everything to one side and we're done. So I'm going to move the 3n squared over. I'm going to combine these together to get 5n, and then I'm going to move it over. So minus 5n. And we have 2n cubed plus 3n squared plus n equals 6 summation I equals 1 to n I squared. The left can factor. I can take an n out, and then I can factor it as 2n plus 1 times n plus 1, and then divide by 6. And lo and behold, we have proved our result. Okay, so this is another result we're going to need when we start doing the ultimate goal of showing that the area under some curve is the summation of infinitely skinny subintervals. Again, just because I think it's interesting. Sorry you're along for this ride with me. But if you're going on to math in college, this is the type of stuff you do. This is an algebraic type proof, I guess, dealing with summations. Summations come up a lot second semester, so that's why I don't mind devoting time to this. It's nice to start getting more comfortable with summations. So it's actually showing you something I think is interesting and helping you out with summations. All right, so that's the end result. I may ask you some questions about this whole thing in this discussion to follow.